Okay, still looking at buffers and how they behave and how you can make a buffer without meaning to in some cases. What we've got here is a solution that is full of sodium, don't care, and acetate or ethanoate. So up here the solution contains a whole bunch of CH3COO minus. And they add hydrochloric acid to that, which is to say they add H3O. Now, ethanoate is a weak base, so it makes sense that the initial pH is above 7. And as we add acid to it, the pH is going to drop. That's not surprising either. When we start doing this, though, we turn some of the ethanoate or acetate into CH3COOH because it gains hydrogen from the strong acid. And we get water at the same time. This water is from the hydronium that dumped a hydrogen and it's still there. And then the acetate picks up a hydrogen and becomes acetic acid or ethanoic acid. Once that happens a little bit, our solution will then contain ethanoate and ethanoic acid, which is to say it'll contain a weak base and its conjugate acid. This mixture forms a buffer. And so we don't have a buffer at first because all we have is the ethanoate. But once we've created a little of this, then we do have a buffer and the solution starts stabilizing. You're adding acid here and thinking, geez, why is it taking so long for this to drop? It's because you have a buffer solution now that's resistant to pH changes. They ask us to label where the region of maximum buffering is, and this flat region is where the buffering is occurring, and roughly in the middle of it is where you would see maximum buffering. We say that because if you're way over here, your solution contains plenty of CH3COO, so it's highly acid resistant, but you haven't put in any of this yet, so it isn't very base resistant. If you're right over here, then the acetate is pretty much exhausted. You may have a lot of acetic acid, but you don't have much acetate anymore, so the acid resistance is no longer very strong over here. But right in the middle, you have some ethanoate or acetate, and you also have some acetic acid or ethanoic acid. That's where the buffer is best able to stabilize the pH because it has a mixture of these two things. Over here, it's all CH3COO, meaning it can resist acid but not base. Over here, it's all CH3COOH, and it's pretty much out of ethanoate, so it can resist uh, base but not acid anymore. The center is the ideal point, or the point of what we call maximum buffering. The pH is the most stable there. The equivalence point that they ask about in Part C is the same one we've been finding in other titration curves. You look for where this curve is dropping the most steeply, and you mark the middle of that drop. I'd say around there would be our equivalence point. And the equation for the titration, we got it here. Okay, more stuff about buffers. Why do we need buffer systems in our bodies? Well, there are a lot of chemical reactions in our physiology that only work under a certain narrow range of conditions. They need a specific temperature, which is why we have a fixed body temperature that we can't get too far away from. And a lot of our physiological processes are very sensitive to pH. In particular, our human red blood cells only exchange oxygen correctly around a pH of, if I remember correctly, it's about 7.4. If you go up or down from that pH, even as much as zero point 0.1, the reactions that allow your blood cells to pick up oxygen and then hand it off to cells start to work inefficiently. There are medical conditions called acidosis and alkylosis that occur when your blood is either too acidic or too alkaline, and those things can become fatal very quickly. So our pHs must be regulated very carefully, and that's why we need buffer systems, because physiological processes in us are very finicky about their pH. List some of the body's buffer systems. You can search up examples for this pretty easily, but certainly one of the big ones is bicarbonate or hydrogen carbonate ion in the blood. There is also a system that involves the phosphate ion. Now, the phosphate ion by itself is not able to buffer, but if you mix it with hydrogen phosphate, HPO4 2 minus, that's a buffer pair. You've got a weak base and its conjugate acid. Or mix this with dihydrogen phosphate. Now you've got a weak base and its conjugate acid. In theory, you could even do this with dihydrogen phosphate and phosphoric acid, although I don't think that's present to any appreciable degree in blood or anywhere else in the human body. But any pair from this chain could constitute a buffer system also, and there are others with more complex proteins whose formulae I do not know that serve as buffer systems as well. So a lot of different body functions require a specific pH and have specialized buffers that help maintain those pHs. Which of the following mixtures could act as a buffer solution? You remember the definition for a buffer mix, or the standard way to make a buffer at least, is to mix either a weak acid with its conjugate base or a weak base with its conjugate acid. So here we have HF is a weak acid, but this is not its conjugate base, so this is not a buffering system. Also, neither of these has the ability to absorb hydrogen, so that doesn't look promising as a buffer. Here we have a strong base and a strong acid. That's not going to do it. Here we have carbonate, which is a weak base, and then we have ammonia, which is another weak base. There's no acid in here, so this shouldn't have any buffering capability. And here, if you dissolve this in water, the sodiums are going to pop off, which is nice because we don't care about those anyway. And what you get here is H2BO3 is dihydrogen borate, and its conjugate base is the hydrogen borate ion, HBO3 2 minus. This is a perfectly nice buffer pair. This could absorb hydrogen, turn into this. This could give away hydrogen, turn into this. That's exactly what a buffer system is supposed to do. Okay, looking at another application of this where we get back to equilibrium constants for a little bit. They give us a reaction here where we have ammonium, a weak acid, and it's dissociating just like any other acid would. It meets water, it gives the water hydrogen, so the water turns into hydronium, and having given away a hydrogen, it turns into ammonia. Now, we can write an equilibrium constant for this, and what prompts us to do that is they're talking about a system at equilibrium, and then they give us a bunch of concentrations. So we can write a K for this, and it's the products over the reactants. None of these have coefficients on them, so there's not going to be any powers. Just H3O, NH3. For reactants, we have ammonium, and we don't count the water because water is a liquid, and we only count liquids if the whole thing's liquids. Whoops, sorry, NH4 plus. Now, this is exactly the K that we would use for the acid constant of ammonium, right? It's products over reactants. So we can look up what number this is. If you find ammonium in your data book, its acid constant is 5.6 times 10 to the minus 10. So that's good. If we know two of the concentrations here, we should be able to find a third one. They're asking for the pH of the solution, which we could get because it's negative log H3O. So I have a feeling our question is going to be, find the H3O in this thing, knowing the other two concentrations. Now, usually, when we write an acid constant, we assume that these two numbers are the same because the acid releases them in equal amounts, but that may not be the case here. We have an amount of NH3 given and an amount of NH4 given, so these don't have to be identical. You could have a solution where the acid made some NH3 and then you added some more on your own. So we won't assume that these two numbers are linked, and we'll just solve for H3O. Don't know H3O. The ammonia concentration is 0.35, and the ammonium concentration is 0.25. This solution also releases some chloride ions, but in an acid-base context, we don't care about chlorides. They're a terrible base. They don't do much of anything. So that equals 5.6 times 10 to the minus 10. Now, if we want to solve this for H3O, we can do that if we multiply by 0.25 and divide by 0.35. That'll cancel those other numbers. And of course, we must do that on both sides of our equation to keep things fair. So now our 0.25s cancel, our 0.35s cancel, and we end up with H3O equals, and out comes the calculator, 5.6 times 10 to the minus 10 times 0.25 divided by 0.35. I find that the H3O concentration is 4 times 10 to the minus 10. If you negative log that, you get that the pH is, I get 9.3979, but it looks like this should be to two significant digits, so 9.40 should be our pH. So if you think about Le Chatelier's principle here, this reaction looks like, because it's got a weak acid in it, the pH should be below 7, but what's happened is they've put in a large amount of NH3. If you put enough NH3 into a system, raise that a whole lot, what does the system do in response? It uses up NH3, and it uses up H3O, and it produces excess amounts of ammonium and water. In other words, if you add enough NH3, you can force this reaction back to the left so that it uses up H3O and produces ammonium. You can drive that reaction away from the acid side. I believe that is what's going on when you get a pH of higher than 7. It's this ion effect, or in some cases, I believe it's called common ion effect, where adding excess ammonia can shift the equilibrium. It's an instance of Le Chatelier's principle where you add excess of a chemical to shift the reaction to the other side. So, little weird that we start with NH4 and end up with a pH above 7, but that is what happened. Okay, one of the buffer systems in the human body. It looks like the standard example where we have carbonates in the blood. Okay, so here we have hydrogen carbonate acting as a base because it's taking hydrogen, turning into its conjugate acid, and the other reason we say that a base is forming is that it reacts with water and produces OH. So if we have this system, we have a container and it contains HCO3s and H2CO3s. What happens if we add vinegar to it? Vinegar is an acid. It wants to give away hydrogen. This cannot take any more hydrogen, but this can. That's probably the strongest base that we have in this system, and so hydrogen carbonate ion as a base can react with the acetic acid or ethanoic acid. This gains a hydrogen and becomes carbonic acid. The acetic or ethanoic acid gives away a hydrogen. And there we go. This reaction turns a relatively strong acid into a weaker acid, so it's an effective way of stabilizing the pH. That's what we've seen buffers do. So they say, oh, okay, it took me a while to realize this is multiple choice, sorry. They say this system will respond to the addition of vinegar by, well, doing this. So which of these describes the reaction we just wrote? Replacing vinegar, that's the ethanoic acid, with hydroxide ions? Nope, that doesn't happen. Reacting the vinegar with carbonic acid. No, these do not react with each other. They're on opposite sides of the arrow. Shifting the equilibrium to the right because hydroxide ions would increase. If we do this, it takes away, I think this is Le Chatelier again. If this reaction occurs, then we are decreasing HCO3 and we're increasing bicarbonate. What would the system do about that? It would try to replace HCO3 by using up H2CO3 and using up hydroxide. That doesn't shift the equilibrium to the right. It seems to me this reaction would shift the equilibrium to the left. When these go down, the system reacts by shifting to the left, but that doesn't produce more carbonic acid. What are they doing here? This reaction does produce more carbonic acid. Is that what they're talking about? Okay. I think this makes sense if we say this reaction occurs and produces more carbonic acid, and then we think of that as our stress. The buffer system, when you add vinegar, the end result, or not the end result, but the consequence of that is you produce carbonic acid. And then the system's response to that is carbonic acid reacts with hydroxides, and that shifts the equilibrium to the left. So I'm not delighted with that answer, but I feel like shifting to the left and producing carbonic acid is the only one that makes sense here. Definitely, adding vinegar should not cause hydroxide ion to decrease. Okay, maybe it does. Sorry, I'm fine on what the buffer actually does. I'm just having some trouble wrapping my head around the options that they're giving us in this multiple choice. If we have this system and we add vinegar to it, let's actually forget about my buffer. I think that might be harming more than it helps. If we have this equilibrium in the blood or wherever, and we add vinegar to it, CH3COOH. This is an acid. It will react with the strongest base it can find, which is the hydroxide. Those will react and form acetate and water. What that means is the amount of hydroxide will decrease. So that's the effect of our stress. It takes a few steps to get there, but adding vinegar deletes hydroxide. So as far as the system's concerned, the amount of hydroxide just got reduced by something that we did. How does the system respond? It wants to produce more hydroxide. At the same time, it produces carbonic acid, and that uses up hydrogen carbonate and water. So that would mean the system shifts to the right because hydroxide ions decrease. I think this is what they're looking for. So because we just covered buffers, I was trying to write a buffer reaction and work with that. But it seems like this question is better handled with Le Chatelier's principle. You just work with the equilibrium they've given you and say adding vinegar will cost you OH. The system will try to replace the OH. So sorry about that. That took a few tries before I got going, but I think that is the thought process they're looking for. Okay, what do we got here? An important buffer in the blood is, okay, similar reaction, carbonic acid. A sample of this at equilibrium, okay, they're talking about equilibrium and giving us numbers. I feel like we need a K here. The equilibrium constant for this will be H3O. That's one of our products. And the other product, I think this has got to be HCO3 for this reaction to make sense. HCO3 minus. For the product or reactants, we have carbonic acid, H2CO3. We don't count the water because it's a liquid and the other things are not. Now, this reaction is the acid constant for H2CO3, right? This is exactly what it looks like when H2CO3 acts as an acid. So we can use the number out of our data book for H2CO3, which is, looking for it now, 4.5 times 10 to the minus 7. So there's our K. And it looks like we have two of these other concentrations, so we should be able to get the H3O. Probably, perhaps. HCO3 is 1.1 times 10 to the minus 4. H2CO3 is 1.2 times 10 to the minus 5. 4.5 times 10 to the minus 7. So, if we want to solve this for H3O, we'd want to multiply both sides by 1.2 times 10 to the minus 5 and divide by 1.1 times 10 to the minus 4. And over here, we're also multiplying by 1.2 times 10 to the minus 5 over 1.1 times 10 to the minus 4. If we do that, these 1.2's cancel, the 1.1's cancel, and we're left with H3O equals a number I'm going to calculate in just a second. Let's see, 4.5 times 10 to the minus 7 times 1.2 times 10 to the minus 5 divided by 1.1 times 10 to the minus 4. Well, it's a good thing we only need two significant digits because that's all my calculator is giving me. 4.9 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, negative 8 it looks like. That should be our H3O. pH is negative log of that number, and that comes out to two significant digits, 7.31. So, ugly numbers, but still just working with an equilibrium constant. So, hopefully not too big of a deal.